Great, hi everyone, welcome to our colloquium. It is my pleasure to introduce Caterina, our own Caterina Vernieri. She's from currently faculty in the PPA division at SLAC. And she got her PhD from the University of Pisa in 2014, then was at Fermilab, then came here as Canopy Fellow, and then moved on to PPA faculty. She's going to tell us about the Higgs Boson at future collider. So thanks, Caterina.
Thank you, Lauren, and thank you all of you for being here today. So I can tell you a little bit about my research area and something I've been very excited in the last period in order to understand better where we are with collider physics after the Higgs boson discovery and how the Higgs boson plays a central role to move forward in planning for the future colliders that hopefully one day we will build. So I'm pretty sure you are familiar with this slide in all the fun animations I'm going to go through. The reason why I still like to start from this point of view because it's an unwilling reminder as we go forward in the talk and understanding what kind of technology we have to develop in order to increase our understanding of nature is that at the end of the day, most of the universe is made of things we don't really understand, dark matter and dark energy. Ordinary matter is only 5% of it. That we have a framework now, theoretical framework that has been developed with experimental data, and it came to be in the 60s, the standard model, that tell us how the fundamental block of matters that have been discovered and the fundamental carriers that describe the interaction between these particles can explain the data and the matter the ordinary matter that makes up only 5% of the universe. And this picture here, that is like our periodic table of particles, was just benefit one addition recently with the discovery of the Higgs boson. And the goal of my talk today is to tell you where we are in understanding the Higgs boson, why it is so mysterious to us, and what kind of strategy we can set in place in order to use it, in order to delve into the unknown in trying to find what is missing in the standard model and how we can explain more than the 5% we can explain so far. So again, the starting point is 4th of July 2012, where the Higgs boson was discovered at a particle collider. I will tell you more detail about it. And that was like a success of the theory because it was first theorized by these two gentlemen in the 60s, and then only years later, 5 decades later, was actually discovered, and that was a complete success of the experiment and the theory. But then, since then, now we are on our own to try to find new physics, and one of the things that's remarkable is that so far the data really matching the expectation. So we need to better understand this particle and see what it can tell us about the things that the standard model cannot explain. So what is the Higgs boson? Higgs boson is a manifestation of the Higgs field. And the reason why it was first theorized is because in the standard model, there was no mechanism for the particle to acquire mass. So Peter Higgs and others then theorized that you have an Higgs field, which is always on and permeates the space and time, and it's always on at any point in time. And the particles interact with the Higgs field and slow down. So stronger is the interaction, larger is the inertial mass they acquire. So it's a very specific field, like with this property, it is always on. There is not such a thing in any other field that we have describing the other interaction between particles. So the Higgs boson then is a result of this. And what we are doing now is to understand how it interacts with all the other particles in order to verify this mechanism that, the interaction with the particle is proportional with their mass and many of the other properties that are surrounding the nature of this field, why it's always on, why it has these properties. This is something you do at Collider. So this is something where you have basically, you start with protons, which are very light particles compared to an Higgs boson, and you collide them at almost the speed of light. Then special relativity is telling us that then the energy can be converted into mass. So by having proton colliding at very high energy, you can make something more massive than a proton. So that's the way that the LHC and the experiments of LHC were designed to be in order to be able to detect particles that were massive, like the Higgs boson, something more exotic that will be a signal of a dynamic beyond a new particle that could describe a new dynamic in the standard model. So we have proton-proton collisions happening once every 40 megahertz, which is 40 times million per second. And we have two apparatus that are set into the interaction points. Overall, the protons are interacting in 4 different points of LHC, and we have 4 cameras. But only 2 of them, CMS and ATLAS, were designed in order to really probe Higgs physics and discover new particles, new massive particles at LHC, and test the standard model in all its properties. So CMS and ATLAS have been designed with different technologies, but they all come with very similar performance to provide us a very high, good quality data to really understand the proton-proton interaction. So one more thing I want to tell you is about how much data we have. So when we first discovered the Higgs boson, we were, first of all, a 7 TeV, center of mass of energy. Since then, the machine has been upgraded to run at first at 8 TeV, then 13 TeV in 2015. And now we have a little bit of addition, 13.6. And we have accumulated a huge amount of data since the Higgs discovery. So the Higgs discovery was achieved with roughly 10 inverse femtobarn. Right now, we have a factor 25 more than that. So this is really enabling us not just to test all the possible theories beyond the standard model that highlight new signature at LHC, but also have accumulated so many Higgs bosons on our tape that we can also start understanding its property with increasing precision. And indeed, now, for instance, one thing is that in the theory, the Higgs appears with a mass, and the mass is a free parameter of the theory. But now our level of understanding of the detectors and their calibration, as well as the large amount of data we have collected, has enabled an extremely precise measurement of the Higgs boson mass. This is, if you look in the PDG that collects all the possible particles that have been discovered so far, you see that Higgs appears as a scalar with a mass of 125 GeV and an accuracy on this measurement at the level of less than per mil. And this is amazing due to, and this really pays off the incredible work has gone into modeling and calibrating the detectors for both ATLAS and CMS. So as I told you at the beginning, one of the peculiarity of the Higgs mechanism is that it interacts with all the particles with a proportionality given by their mass. Larger is the interaction, larger is the mass. And so we have a lot of data now. We have looked at all the possible ways that we can produce Higgs bosons at LHC and all the possible decay modes. Once the mass is set, we can predict exactly all these properties. Then by measuring all the decay modes and the production mechanism, we can test how the Higgs interacts with the other vector bosons, with the fermions. And we've been able to measure some of these decay modes and production modes and convert that into how much we understand the strength of the interaction of the Higgs boson to each of these particles. So I really like this plot for 2 reasons. First of all, I'm going to tell you what it is. It shows you at the x-axis you have the mass of the particle, and the y-axis is the strength of the interaction. So this is showing the proportionality. So each data point is a different particle interaction with the Higgs boson, and as a function of the mass, you see the proportionality of the mass interaction that is intrinsic of the Higgs boson mechanism. So this shows a great success of the theory up to this point because we see a linear, right, as we were expecting from the theory. But it also shows an opportunity because if you look at the data points, first of all, not all the particles are represented. The light particles are not yet tested. For instance, the interaction with the electron, with light quarks. The interaction with the charm quark has a huge error bar, and also the interaction with the bottom. And with the muon, have a larger bar, like the error is of the order of 20% or so. So 20% for the B, 30% for the muon. So this is an opportunity for new physics. So within the experimental error, it seems everything is compatible with the standard model. But then we know that the standard model is incomplete. We know that the standard model doesn't explain everything. And there might be room in the Higgs sector for new physics. And within this error bar, there might be room for something that is not captured yet from the theory. So that's why I like this plot for two reasons. Confirm the standard model, but it leaves hope for something beyond it that we can test at colliders. Another thing we are testing, and it's important for us to understand better, is the shape of the potential. So the Lagrangian here, you're all familiar with in the contract form because CERN put that into a t-shirt, so it has become almost mainstream. So after the Higgs discovery, we are testing the last two lines of this Lagrangian, right? The first line is interaction with the other particles, and we saw the other plot is a good summary plot of where our understanding lies in terms of testing that. The last line is the Higgs field potential. And the Higgs field potential is the one that enables, the shape of the potential enables the electroweak symmetry breaking. And but it also has a lot of connections with the phase transition that happened early in the universe in order to give the Higgs field these values that are completely defined in terms of the mass of the Higgs boson and the vacuum expectation value. So in the standard model, this is totally defined, and we can predict it and we can test it by analyzing and looking for events where we produce two Higgs bosons. So once we know the mass of the Higgs has been very well measured from our experimental data and knowing the vacuum expectation value, we can predict everything about this, and we can go and test it by measuring double Higgs production. But why it has this shape? It's not derived from first principle, and it's connected to the stability of the universe, the evolution of the universe. So any new physics would hide in the shape of the potential. And that's something that it's very tantalizing, and we want to test better because it can provide insight of what it is beyond the standard model. So this is all in a nutshell why people are very excited at colliders to measure double Higgs potential, double Higgs boson production, because it's the first order way to probe the shape of this potential that's deep implication with cosmologies and baryogenesis. Now, I don't want to spend too much time about LHC, although most of my time is on ATLAS, like Lauren and others here in the room, working on LHC data. I just want to tell you what I expect that LHC is going to teach us beyond what we already know on the Higgs boson, and how we are using that ignorance that we are going to be left with after LHC has been shut down, to think about the next machine we want to have in order to learn more about the Higgs and its connection to the fundamental question in particle physics. So right now we are in LHC. As I told you, we started taking data at 13.6 TeV, and we are just accumulating data. These are very rare events. We produce, once in a billion collision, we produce a Higgs boson. So we really need to have a lot of collisions in order to have enough statistic of enough Higgs bosons to go after the precision and the measurement we need to have in order to test new physics contribution. At a certain point, next couple of years, we're going to go into a shutdown. We're going to replace our detectors to be ready to take the most advantage of the high luminosity era of LHC, where we're going to run the machine at higher intensity in order to collect data faster at the same energy, just more statistic. And that is going to enable us with basically multiply by factor 10 the data set that we're going to have before the shutdown. So a factor 10 increase in statistic in order to improve many of the Higgs physics measurements that are limited by statistic. And right now we're busy, especially here at SLAC, building the next generation of detectors. In particular, SLAC, we're building the inner system, which is the pixel layer silicon detector that is right on top of your beam pipe at LHC. And the idea is that with enhanced precisions, we can take most out of the high luminosity data. That will be, in order to accumulate a lot of data in less time and have our factor 10x in statistic, we're going to run a very high intensity. Collisions would look like this, a very dense environment. This is a Z view from the beam pipe where you see all these dots are multiple interactions that are happening at the same bunch crossing. So we collide bunches of protons, 40 megahertz, and out of very dense bunches, we have a lot of possible interactions that will give us high density of particles. And we need to have high resolution instruments in order to make the most out of this statistic and be able to identify Higgs bosons interactions out of a lot of QCD events that you might have at HC. So that a dedicated colloquium per se. I only wanted to introduce you that to show you the challenge of taking data at HC. And we have to really have high intensity collisions in order to be able to collect enough statistic of Higgs bosons. But if everything goes well with the new detectors and assuming improved reconstruction that can help us coping with the high dense environment of ILLUMINATE-C, then what we expect, this is a projection under some assumption, of the same plot you saw before, but now assuming all the statistics that we can have a factor 10x more of the plot you saw before. So again, particle mass versus measured strength, you see all the errors are shrinking. And if you look at the ratio plot now, you see that the error bars are getting much smaller. So what we expect is that high luminosity can enable us to improve by a significant factor precisions on most of the coupling measurements. And we are going to probably have 2 to 5% precision to many of the Higgs couplings. The charm and the strange are not shown here. The strange is for sure out of reach. And the charm has not been projected yet into these assumptions, but I expect still will have sizable uncertainty or the order of a few 10%. In the soft coupling, the Higgs production, the soft coupling, the pair Higgs production will have a 50% uncertainty on that measurement. It's a very rare process, and even with a lot of more statistic, what we think is that we're going to do ballpark 50% uncertainty on the measurement of that specific coupling. So is that enough to do precision measurement and probe new physics? And the answer is no. So, and I'll try to convince you why no, why we need something more. So I'll pick two set of plots. First, I want to start from the comparison of these two. So my argument for you is that with no new particles found at LHC and level of 5 to 10% uncertainty on many of the Higgs coupling, there is room for new physics. And we need to measure the Higgs couplings at a much higher precisions to understand the scale of new physics. One way to help you visualizing this, I selected these two plots that shows the deviation expected on some of the Higgs couplings in two different new physics scenarios. In one case, on the left, you have a supersymmetric model. On the right, you have a composite Higgs model. The first thing you notice is the size of the expected deviation from the standard model prediction. Is the level of percent to sub% in some cases, and most 5%, which is much lower than any precision high luminosity can probe. And you might think you cherry pick these plots. No, most of them, they look like at this point, predict percent to sub% deviation in the Higgs boson coupling. Because remember, LHC has done a lot of searches for new physics per production of new particles, and all with no result. So we have also those upper bounds that is telling us that if new physics exists, is in this particular phase space where mass up to a few TeV, for instance, has already been probed. So you have to go high in energy if you're thinking of an additional singlet. So this is one argument that expected at this point, given that direct searches for new physics at LHC in the phase space that is allowed to LHC to test is giving no result. And the precision we can achieve at LHC, we need to go and measure at the couplings at percent to sub-percent level to be able to find the pattern of new physics. And depending on the level of deviation in which coupling, we can differentiate which kind of new dynamic might be beyond the standard model. Might have an additional singlet, might give an additional doublet, and will appear different in our data with a different pattern of deviations. Second argument I have for you, it's a way to visualize the same data in a different way. So now we are in a specific model again, and in this specific model you expect your additional Higgs bosons, and these lines shows, depending on the coupling and assuming the precisions you can have future colliders, what kind of reach you have in this specific model. And you can do that for different models, and you see that you are extending beyond LHC in terms of mass reach and coupling reach. So that precisions can indeed be adding on top of direct searches at LHC in order to test new physics. And how we can achieve precisions? The only way to achieve precision is to change initial state. So I showed you that at LHC we are limited by data because making Higgs is a very rare event. Most of the time when you collide protons, you make other things, a lot of jets, and only 1 in a billion events you have Higgs bosons. So we can change that if we go at A plus and minus. So if you start from electron and positron, then you have a high probability of making a Higgs if you collide them at 250 GeV. And then you have an initial state that is very well defined and with high polarization in principle can also yield to high precision measurement. And the argument I want to give you to show you how more designed for precision is the E plus and minus environment is by comparing two images. One is from LHC, how an LHC event where a Higgs is produced looks like in our detector. This is transverse view, so you have to imagine the beam coming out of the screen at the center. So in this case, you have the final state particles out of the Higgs production are overlaid on top of everything else is happening at every collision you have LHC. You have other multiple proton-proton interaction, you have underlying events. It's a very dense picture. On the right here, you have a simulated Higgs event at E plus and minus, and the only particles you see are the particles from the Higgs final states. So this is really enabling, you can see just visualizing as an argument, possibility of collecting more events that are clean. There is no ambiguity what was being produced, and that can really aid to produce to very precise measurement of the Higgs boson properties. And one other thing to point out is at LHC, because we produce way more things that we need to record, we do make selections online in order to, if we were to record everything that happens every 40 million seconds, we have a collision, so we won't have enough storage or computing power to process that. So what we do is select online whether or not a collision seems interesting, and we only preserve the collisions that are interesting. In a collider environment like E plus and minus, where most of the time something is interesting happening and you don't have as much rate of particles and it's more manageable at each collision, then you can record everything. So if there is any new physics signature that has gone undetected at LHC, at E plus and minus, you will be able also to detect that as well. Something unexpected that we had not designed our trigger system for. So how does Higgs being produced at E plus and minus? Energy is key here. So depending on the energy you have available when you're colliding your E plus and minus, you can access Higgs production in different mechanisms, and then you can probe different kind of interaction. So starting at 250 GeV, the main production mechanism is when the Higgs is produced in association with a Z boson. And I'll tell you why this is a very interesting way to really calibrate in a model-independent way the Higgs boson width in a second. As you increase the center mass of energy, then most of the time Higgs is being produced in vector boson fusion, double fusion, sorry. And then as you reach 500 GeV and above, then you can also access the Higgs production in association with a TT bar pair. And that's interesting because then you can start testing. It's the only way to test the Higgs coupling to the top quark. And around the same time, above 500 GeV, you can also start enabling double Higgs production. That, remember, it's interesting to test the soft coupling, which is key to test the Higgs boson potential. So energy is key. So depending on the energy you have available at your future collider, then you can test different production mechanism and complement your measurement with what LHC will have at that point. The reason why it's very exciting at E+T minus at 250 GeV, the ZH production mechanism, it's because you can use the so-called recoil technique, where you basically have now your Higgs being produced with a Z boson. You measure everything about the Z boson. Your initial state is very clean, so you know what to expect on the other leg of the Higgs. And that's a very powerful way experimentally to calibrate, to measure inclusively the Higgs with no more assumptions on possible decay modes. So it's a very good way to test, for instance, exotic decays of the Higgs or the invisible decays of the Higgs as well. Because complementing this with the measure of the total rate of events in the cross-section of ZH, you can really get away with measuring precisely the Higgs boson mass and improving over the measurement at LHC. Now you can go one order of magnitude better than LHC, the level of 0.001%, and measuring inclusively the total width and be able to set very precise measurement on exotic decays of the Higgs. Because what at LHC we do, we know from the theory how much is the branching fraction on each particle, and we test that. Here we can actually, with this recoiling technique, do one step ahead and just measuring inclusively all the Higgs decays like that. And this is really key because we know the initial state and it's everything well defined. Another thing that it's a great opportunity that opens up when you have a E+T minus initial state is the ability really discriminating between different decay modes of the Higgs in the hadronic final states. So when Higgs decays to B quarks and C quarks, what we do at LHC, it's like to distinguishing between a bunch of other things that are produced at the same time, including pileup, is to try to find to measure the lifetime of the B hadron and C hadron that originated by the hadronization of the B quark and the C quark. That's a very challenging task for B quarks, but we have been able to do that very successfully with machine learning that is aiding us to really use all the information within a jet to understand an image of how a jet coming from a B looks like and distinguish that from light jets initiated by U and D and gluon, and to a certain extent from strange as well. The B to C discrimination at LHC is very challenging because the lifetime between a C hadron and a B hadron is not that different. In between, if you add all the confusion terms for additional tracks you have, the discrimination between B and C is not that great. That's why there was a large statistical uncertainty error bar on the measurement of the Higgs to C coupling. More data can help, more sophisticated technique will help. We will improve on that. But it's not that we can measure the C coupling at percent level at LHC. Distinguishing C and B from strange is even more challenging because our signature to discriminating a strange quark initiated jet from a light initiated jet is basically the only kaons that you might produce out of the strange hadronization. But you have strange also from B and C. It's very challenging to do at LHC, but the E+T minus has been demonstrated at SLD here at Stanford that you can do it by having dedicated detectors, gaseous detector that are designed to detect those kaons from the strange decay, and then coupled with all the techniques we know also from LHC about how to distinguish the B hadron, reconstruct the B hadron and the C hadron, then all combined together you can achieve good performance not just to discriminate B and C, but also identifying correctly Higgs to SS bar decay. So going after the light decay of the Higgs as well, and exotic decay of the Higgs like BS or CS and so on. Probing new physics in the flavor decay modes. The Higgs is important. Again, as I told you, higher in energy, in the plus and minus than we can make per production. And we have different mechanisms, either DHH, higher energy we have through W fusion, and then we make two Higgses that way. The good news is that if we also can use polarized beams, then we can also enhance the cross-section by making an effective use of our data taking. And I'll show you in a second what to expect the precision to be on this measurement of future colliders, I plus and minus collider. But one point to make is that those analyses are based on simulation and projected sensitivity of detectors, projected performance of the detectors with very simple reconstruction techniques. So importing everything we have learned from LHC in these analysis can actually help us really understanding the potential of those data. So this is a plot I use as a reminder that there is a lot of work to do to really understand the potential of future colliders. He shows current state of the art of expected performance in reconstructing E plus and minus event into DHH, looking at a specific final state where both Higgses are decaying to big quarks. And that is like in the red curve is actually what is a truth level. So what actually you should expect if you were able to identify correctly all the Higgses and measure everything. So there is a gap between what we think we can do with current detectors and current reconstruction performance and what actually we will be able to do in an ideal world where we get everything right. So there is room for improvements in detector performance, but especially in reconstruction technique to really improve even the projected sensitivity and the potential, fully explore the potential of the data that we might have available. Now, I want to shift gear a little bit. I told you, I hope in a convincing way that there is a lot to learn at LHC about Higgs physics, but even more to learn if you want to test new physics and learn more about the nature of new physics through precision measurement of the Higgs properties. And E plus and minus is the initial state I'm suggesting. And there is two ways you can achieve E plus and minus colliders, linear or circular. Linear, you have your electron and positron bunches, you collide them once, one interaction point, and in this way, you don't really suffer much from synchrotron radiation, so you can achieve high energy, you can polarize the beams. And you know that if you can polarize the beams, then you can increase your cross-section by selecting the right polarization for the electron and positron. You have only one interaction point. And what people have been thinking is that if you want to design a detector that are having different technologies, targeting different measurements, then you can push and pull and switch your detector during the data taking after some period of data taking. Alternatively, you have a circular machine. So you build a ring, you collide electron and positron. At this point, you collide them continuously, so you can achieve very high luminosity. But now you're limited by synchrotron radiation, so you cannot go higher energy than 350 GeV roughly. But you can have multiple interaction points. So like at LHC, you can have 2 or more detector designed with different technology to test the same physics that can cross-check each other. And of course, the community has been developing over the last few decades proposals for each one of this. ILC is probably you probably have heard of that, has been around for a long time and is designed to run in Japan. Initial stage of 250 GeV, so 250 it's where we do a bunch of measurements of the Higgs with the ZH production mode. And then being upgraded later at 500 GeV, so you basically expand the length of your collider to increase the energy. And then when you can test double Higgs production, DTH, and so on. And then the circular machine is, the two circular machines that are being proposed, one is in China and one is at CERN, CPC and FCC. And they both expect to have a first initial stage with the electron-positron collisions in a ring which is roughly 100 kilometers long circumference. Initial stage of 240 GeV, and then later on being upgraded with protons so that you can run roughly between 90 and 100 TeV proton-proton in order to go high in energy, because you cannot go higher than 350 with electron and positrons. Other two alternatives for linear collider were discussed and presented as NOMAS, which is our ATP community exercise that went on a couple of years ago, ended a couple of years ago. One is the Cool-Copper Collider with a new technology that I'm going to refer to later. That is it was devised in order to deliver the same physics as ILC, and CLIC that instead was designed to run high energy and reach even 1.5 TeV. Later last year, in December, there was a community process, NOMAS, led to a prioritization panel, the P5 report, probably you have heard of that, it was in the news as well, that selected of the old proposals two as more feasible to move forward, and encouraging US participation, either ILC or FCC. These are both offshore facility, and encouraging our contributions to either of these machines and the studies that will lead to eventually at least one of them. So now, of course, we can, as I told you, we can project our sensitivity and see how much better we can do at this future collider machine. And the community has basically agreed that the physics output of A plus C minus, either linear or circular, 250 GeV, is very similar. So if you go and actually inspect and look carefully at the run plans, you would see that one, the linear collider, because it cannot run at very high luminosity, will only deliver 2 inverse autobarn. And the FCC instead is planning to deliver 5 inverse autobarn at the Higgs. But because in linear collider we can use polarization, in circular collider, then we only have the luminosity upgrade. Once you plug that in, the data, the projected sensitivity is basically showing that the first stage, linear and circular, can provide the same physics. And if we look at the number, you will see that there are sub-percent level precisions, percent per level precisions to most of the couplings. So this is improving order of factors in most of the coupling with respect to the best that a high luminosity can project. So I hope this slide, this table, it's crowded. The only thing I want you to notice is that the ILC line, the first column for ILC and the first column for FCC have roughly the same numbers, which means same physics potential in the first stage for both machines. And all of those numbers, they look very small compared to what we were looking before at LHC. So for the Z and the WW, we have sub-percent level precisions. And now we have just percent level precisions on the C and the B. And the other bars was pretty large, we saw before. So promising improvements over high luminance C, either ILC or FCC will accomplish that result. Then, if you can go high in energy and then unlock 500 GeV center massive energy, then you can measure the self-coupling through pair Higgs production, and the kind of sensitivity that we project, although I showed you the first slide before, there is a lot of room for improvement, is 20%. And level 20% improvement, according to our colleagues theorists, is enough to really discern if models of electroweak baryogenesis and really understand the nature of the electroweak transitions, and since the Higgs field is playing a big role into that as well. So 20% is the ballpark that they have given to us as a good target to test for precisions for the double Higgs production. Now, going to the end, I don't want to spend too much time on giving you the details about the detector, but I do want to mention that. So once you have such a key initial state, the challenge for us experimentalists is to build the best detector we could in order to really take the most advantage of the rich physics program we might have at this future A plus C minus machine. I say might have because depending on the machine, then you might want to develop one detector which is more suited for low energies. Like FCC will start from running at the Z-pole, for instance, and then going to the Higgs physics. Linear collider, ILC, will go first at the Higgs and then at higher energy. Overall, the intersection of these physics requirements leads to very stringent requirements on detectors. And we have to detect different particles that are produced out of the collisions at E+C- as per LHC. But now we're targeting extreme precision in order to really take advantage of the data we're going to have at E+C-. And once we plug that together, we have requirements for the tracking system that detects charged particles, the calorimeters that detect hadrons and leptons that are, or particles that are being interacting with electromagnetic interaction and hadronic interaction, and then the muon system later on. And once you put all together, this is a schematic, very simple schematic in RZ view where the beam is on the Z line. Of all the subsystems we might have to design and build in order to make the best out of the physics at E+C-. And this is the work that has to start now, because we really have to do R&D on technologies that can help us to make the best use of future E+C- data. With one thing into account, we cannot do the best detector for each subdetector because that is going to be very expensive. So we need to optimize overall performance, having a clear goal in mind of which physics benchmarks we are targeting in order to build the best detectors and under budget. So one example of how you do that, you remember this plot that showed you the beautiful peak for the recording mass at the Higgs? In order to measure the Higgs mass with that precision, we need to really have extremely excellent resolutions on the momentum of the particles. If we want to distinguish, and that's giving requirements on the tracking system and the granularity of my calorimeter. If I want to reconstruct and distinguish B quark from C quarks, I really need to have the best vertex detector I want to dream of, because I want to maximize for my impact resolution precision, and that means I want to have a vertex detector which is very close to the interaction region with extremely high granularity and low material budget, because I want to minimize multiple scattering. So we already know now that we want ultra low mass trackers with high granularity. And the detector R&D has to start now in order to develop technologies that we don't have in hands now to build a detector which is challenging in different reasons with respect to LHC. And going very quickly through this so I can actually talk about accelerator, one thing to keep in mind is that you can tune your sensors but also reduce all the cables and cooling channels you might need to operate your detector. And in order to do that, you put as much as possible into a large array of silicon, and one of the promising technology is MAPS, monolithic active pixel sensors, where you have your ASICs implanted in the wafer where your active sensor is, so that you can scale that with the size of the wafer and achieve ultra thin sensors with a CMOS technique, which is cost scaling effective. And you can achieve thinning such that you can bend your silicon around the beam pipe. So incredible opportunities for detector R&D for future precision at E+C-, where you can wrap your beam pipe around silicon in order to achieve high resolution with low material budget. So now, as I was telling you earlier, we are LHC. High-lumen HC will start eventually in a few years from now. Deliver in 10 years 10x more data, and then we have a little gap before the next Higgs factory will go online, either ILC or FCC. In the meantime, work towards a high energy and technology to get high energy. We heard a couple of weeks ago COLLOQUIUM about the muon collider from TOVA. It's one of the possible technology to reach that high energy. So in terms of Higgs coupling, sorry, where did I go? In terms of Higgs coupling, that's roughly an escalation, educated guess of where we could be depending on which collider we have access to. High LUMI would push down precisions to 5-10% on the couplings and 50% on the self-coupling. And then E+C- can unlock percent and sub-percent precision. And very high energy measuring the self-coupling to percent level. Now, this is a timeline, but there is a lot of things have to happen. Europe has to get together and start building FCC, or Japan has to get together and start building ILC. In the meantime, the report left space for new opportunities and accelerator R&D, which is key to enable the machine of the future. So during SNOMAS, we presented a new technology that was promising to achieve high gradient for E plus T minus collision, and which received endorsement in the P5 report for continuous R&D. So this is some extract from the report to show how the report had put a lot of attention into accelerator R&D to enabling the machine for the futures, and especially demonstrators for these technologies, with an accent on sustainability and making sure the next generation machines could actually also have a sustainability strategy for the future of particle physics. And liquid copper, which is a technology I'm going to cover in the last part of my colloquium, was explicitly called out there. So what that is. Cool copper technology is basically advancement into normal conductive RF, which is basically the result of decade-long R&D conducted at LAC and Stanford for developing high gradient cavities that could achieve high gradient, so high acceleration for electron and positron in less space, basically. So if you achieve high gradient, you don't have to build a long accelerator, you can shorten it. And the reason why I was able to come up with a new design was by solving from first principle what kind of optimal geometry you might have in order to avoid high magnetic field that could disrupt the propagation of the beam, the so-called breakdown rate. So you end up with a design of a cavity which is with a very small iris for the wave to propagate. And then a new solution came made to actually use distributed coupling in order to inject the charge with a phase variation in each of the cavities to allow the propagation of the fundamentals. So this was able to be achieved thanks to use of supercomputing to solve mathematically with accuracy the shape of these cavities and the phase distributions for the propagation. And then you end up with a design that is easy to machine out of slab of coppers because we can modern CNC machines that we can use to inexpensively produce these cavities. So here is the design, and on the other side is one open structure. It's 1 meter long. That it's like the fundamental unit of this next collider. And in the name there is copper. This is the reason. And the reason why it's cool, because independently there's been a lot of work going on in understanding properties of copper for normal conductive RF. And what has been noticed, which is a screenshot here in this study that represents different breakdown over different gradient for different material, different temperature. What has been demonstrated is that copper increased their property, their elevated performance if they're operated cold. But this is not cryogenic cold of superconductive RF. This is 80 Kelvin, which is something you can achieve with a liquid nitrogen bath. So less complicated in terms of cooling and cryo technology that you might need for that. So you operate this cold, and it's kind of easy to design a liquid nitrogen system, and it's cost effective, and then you increase the electrical conductivity of your copper, improve your performance. So you can either operate with the same RF power and double your gradient, or you can reduce the RF power and keep the same gradient. So, and this is basically what we plan to do. To operate this and test these cavities. So when we first decided to adapt this technology for application at colliders, we thought of two possible stages in order to match the ILC physics program. One, to operate a lower gradient, 70 MeV per meter, in order to deliver 250 GeV center of mass of energy. And then, within the same length of your accelerator, just by increasing the gradient, increasing your RF power, going at 120 MeV gradient, in order to reach high energy, 550 GeV. And the overall length of the accelerator apparatus is 8 kilometers now, so a significant small footprint. This plot here, it's not a simulation, these are data. So the gradients have been demonstrated extensively and over a time that is compatible with operations at colliders. What we're planning to do is to further demonstrate that you can put different structures together and accelerate the beam up to 1 GeV. So this is what you achieve in one structure, 1 meter structure. And then you build a carrier module. Our choice is of 8 modules operated together as one element, carrier module, which would accelerate the beam up to 1 GeV. In testing that, really proved that this is a viable technology for collider applications. In the process, we had to learn how to tune the parameters at the interaction region in order for the physics to be interesting and for our detectors to be compatible with the kind of precision measurement that we are targeting at ATLAS and CMS. So we don't just want collisions in a cheap environment with small footprint, we also want high good quality data. So a lot of work has gone into simulating how the interaction region will look like with these parameters for the C-cube beam. And what happened is that you're having now nanometer size beam. It is implied that you have very high density at the interaction point. So for each branch crossing, what you have is production of secondary particles that might end up in your detector, spoiling your resolution. You want to have a very clean image of the Higgs boson, so you don't want to have a bunch of secondary particles spoiling that. So you want to optimize the beam parameters in order to have a good rate of collisions, interesting collisions, but without spoiling too much the occupants in your detector. So all the work has gone into simulating all the beam Stalin processes and comparing with the other collider options, linear collider options, so comparing with the other collider option studies that were more mature in order to calibrate our simulation and understand that eventually how the occupancy in our detector will look like, which is the image here. This is informing also detector design and detector performance, as well as machine development and beam parameters optimization. And this is work that is synergistic with all the colliders as well. So was prompted by developing and informing our developments on the accelerator side for C-cube, but it's also within the community of ILC and FCC, it's all common knowledge that we're advancing together. So as I told you at the beginning, in the report there's also mention about sustainability, and we had done our work in order to understand also how we can operate the C-cube structure in a way that is also more sustainable, meaning less power. So how we can be more efficient and achieve the same physics by reducing the overall power consumption. And we have laid out possible options in order to achieve that. For instance, doubling the length of the bunch or halving the bunch spacing or using pulse compression at the beginning. And each one of these could lead an improvement in power consumption, achieving all of them simultaneously would be a dream, but something that could be tested in our R&D program. Of course, when you talk about sustainability, it's not just operation. The power that you use to operate your collider is also what enters into construction. So we had done an analysis using inputs from the other collider as well to evaluate the impact on sustainability, which is measured in terms of CO2 equivalent that you lose in the environment for constructions and operations. We have compared with all the other options. Of course, bigger is your machine, more impact is coming from construction, but then operations is also significant. And you can see from C-cube between the dashed green and the solid green, you can reduce by a factor if the R&D on those power and consumption reduction ideas would be proven successful. In the meantime, what we are dealing with is to prove that the C-cube technology is feasible for application at colliders with the beam parameters that are providing good physics. And alignment vibration studies, test for single structure are in progress. And this is really work towards the first quarter carrier module, which is under construction now, which would be the first time we would be operating two structures together. That's how it looks like, and it's exactly what it sounds. It's a quarter of the full cryo module that eventually will be the unit on the collider. And just the first step, but really important to understand vibration and alignment performance of these structures for operations at collider. Eventually in the future, if the first step is promising, what you want to do is to use that first quarter cryo module to inject the beam into a full cryo module, and then verify, measure things again, and add 3 cryo modules as a final TDR-ready kind of demonstrator for demonstration at colliders. So this is a technology that is interesting to be developed for, I think, many reasons. Can be served as a standalone collider if the other two are not proven to be feasible, but can serve the other two if they move forward. So I told you about ILC and FCC. So FCC is a circular machine that needs injectors, and it needs 2 injectors at 20 GeV each, and C-Cube could be a viable technology for effective small footprint performing injectors. ILC will need to upgrade from 250 to 500 GeV center massive energy, and C-Cube is a technology that is being considered for the upgrade. And then I told you at the beginning there was that timeline. There is also an energy that we want to achieve. Muon collider is one of the options, and at a certain point in the muon collider accelerator complex chain, you need really to have an high gradient cryogenic system in order to accelerate your muons after the cooling, and C-Cube technology could be possible, an option for that. For advanced accelerator concept like gamma-gamma, you still need to start from electrons, and C-Cube technology could be a good way to achieve that too. So we don't live in a vacuum, so everything we do has to be synergistic and useful to the main goal that we have, build an ATLAS and advancing our understanding for a future high energy machine. And this R&D is, I hope I convince you, interesting and possible serving both purposes. Back to science before I finish. So I usually start my talks with this image. For this colloquium, I decided to end with this image as a final reminder about why we are so pushing for collider physics, the next generation collider. And the reason is because the Higgs physics, the Higgs boson, plays really a fundamental role within all the questions that are left unanswered in the standard model. And the only place to study the Higgs boson is at colliders. Whether or not this is the only fundamental scalar of the theory, there are more. The flavor nature of the Higgs couplings, possible relations of the Higgs boson with dark matter, with baryogenesis. These are only things we can learn more about if we study the Higgs boson properties, and the only place to do that is at colliders. We have a report now that is guiding the spending of HEP in the US, and we have more to come from our international partners, more news to come about ILC and FCC. Either case, we're really pushing towards having a future ATLAS machine to test the Higgs boson coupling. And more opportunities there are now to really design the challenging detectors that we need to have ready to take the most advantage of the ATLAS data. And accelerator R&D is key because for the future Higgs factory and for the future high energy machine, we really need to invest in new technologies in order to provide small footprint and effective performance. Thank you.
Thank you, Caterina. Questions?
Thank you for a wonderful talk. I have a question on these linear ATLAS collider, the ILC and the C-Cube. You mentioned they're triggerless, and wondering if the current technology allows us to store all of the information coming out of the detector, or is there any data reduction on the topic?
So it depends on the data rate you expect. In data rate, it's driven by amount of interactions, primary and beam-induced backgrounds you have, and number of channels of your detector you have to rate. So preliminary studies for linear collider have shown that is completely manageable with not even complex DIQ system. For a circular machine, at the z-pole, when you have a lot of events, when you run at the resonance of the z, maybe some data compression might be needed, or if there are preliminary numbers there, so I don't think simulations are fully developed. I don't think they are talking about trigger yet, but data compression for sure, just to send out the only data you need. Yeah.
Thank you.
Question?
Could you review again? Well, you actually talked about this, but I got confused. What features of the vacuum beyond the standard model one is reaching for with this new generation of alleged, if you build them, the new generation of accelerators? Particularly, I understand the argument for electron accelerators, but now, as far as, I'm a little confused about what spectroscopy of the vacuum you're reaching for, that you're reaching for.
Are you referring to the vacuum or the self-coupling? Because I think the point I wanted to make was that we can measure the self-coupling at a higher energy with pre-production. And the self-coupling is intertwined with the shape of the potential of the Higgs field in the standard model. I'm not clear what you mean by vacuum here.
The standard model is a low energy description of
Yeah.
vacuum, and it has corrections
Yeah.
when you go up. And so is this a fishing expedition for the corrections? Or is there some aspect of the low energy standard model, maybe as at Higgs energies are lower, that you're trying to check or correct?
Okay, I think I understand better the question. So I think here is the potential of the positions on the Higgs couplings and the self-couplings you can have, depending on the energy, a feature plus or minus. So you can probe the standard model prediction on some of the coupling to sub% level, where you expect deviations of that level or bigger. So on the Z, for instance, that could be already finding out patterns of new physics.
Well, okay, I'm sort of following you. So that graph, a particular, if you take the bare standard model, it gives an answer for that. Okay, so you're looking for a deviation?
Yeah. So imagine, like, as you said, a standard model could be taught as an effective field theory, a low energy expression of something bigger than you parameterize as an effective Lagrangian, where the standard model was the lowest order, and then you have increasing addition with a higher dimension operator. In an EFT kind of world, where you effective field theory formalism, where you can parameterize new physics with correction with additional dimensional order, dimension 6 is the next, then dimension 8, we can test those deviations. So we expect, percent level deviations with dimension 6, much smaller at dimension 8, and that's the kind of test one could do. And then what I was showing here was not in terms of SMEFT like kind of reach, because that's very abstract. So I was picking specific models given some deviations. So projecting into a specific model out of EFT, like you go from SMEFT formalism, where you measure deviation in terms of additional couplings, and then convert that into what that means in specific models, which was the plot here. Because you say, I'm expected deviation C6, which is my parameters.
You've answered the question. See, what I don't understand, you can't probably explain, is why one would expect those particular corrections.
Because you might have new physics, and depending on the flavor of new physics, then it would appear differently in the pattern of deviation of your couplings. Yeah.
So maybe a related question. You mentioned that 20% precision on the self-coupling is the target that theorists tell us is helpful for baryogenesis, understanding baryogenesis?
Electroweak baryogenesis, yeah.
Does that mean that, like, if you measure it to 20%, we will know how baryogenesis works?
If it was electroweak phase transition, you can exclude that of phi sigma.
I see.
So it's like enough precision that you can exclude or confirm a saddle model at that point. And hopefully also the Higgs field is like, is affecting also other parameters. So you will have evidence in other couplings at that point of new physics from other couplings as well.
Maybe you could say a word about the motivation for running at the Z-pole for a future collider.
Yeah, that's a good question. The circular collider people, they have developed a run plan to run the FCC machine first at the Z-pole for a few years in a way that you can collect an order of magnitude more Z than lab did to advance precision measurement on most of the electroweak observables, sin square theta W, the Z and W masses and weights, and so on. And it again can prove new physics, proven that the calculations would match the needed precisions, the theoretical calculations will match the needed precision. So the motivation is mostly driven by advancing the knowledge of lab on most of the electroweak observables. But for instance, the CPC machine doesn't plan on a Z-pole run, they will start at the Higgs directly. So it's really something that part of the community at CERN is advocating for, but the community is divided, I would say, whether or not you want to start from the Z or from the Higgs, also because detector requirements for the Z are more stringent than the one for the Higgs. So in a way, you might end up with a detector that is optimal for the Z, but suboptimal for the Higgs. So it's hopefully something to be discussed in the FCC run plans after the feasibility study.
Other questions?
How about, we have some more compact machines, but it's the same technology. Any opinion on some new technologies, like plasma accelerators, laser accelerators, other accelerators?
So I'm happy to hear that you think this is an old technology, because I think C-cube by many is considered as new, and C-cubed here, these new cavities, normal conductive RF operated in liquid nitrogen. I'm happy to hear that for you is old news, but in HEP this is new, that has yet to be demonstrated in order to be feasible and viable as a collider option in multiple structure operation. Then of course you can go beyond that, and I see Tim Barkley there. He has developed a concept where you make out of electron and positron, just electrons, you make photons and just collide photons, and that could be even a smaller footprint. And similar to XCC, which is the gamma-gamma collider proposed as LAC, there is also HALF, which is another concept to kind of, use photons out of electrons in order to achieve higher center mass of energy in a compact footprint. But this is like second order complexity, and it's something that I think the accelerator R&D has to continue to demonstrate these technologies as viable opportunities.
I missed the problem. What percentage reduction in length would you have on linear accelerator using this one?
So let me show you, because I didn't show that, so thank you for the question. So this is comparing click, ILC, and C-cubed. And you have 250 GeV operations, and the difference between ILC and C-cubed, it's between 20 kilometers and 8 kilometers. And the reason why it's 8 for C-cube, it's because it's the same length operated at half the gradient. Once you go 500 GeV for ILC, you go from 30 kilometers to 8 kilometers, because the actual gradient the machine can be operated to is 120 MeV per meter. And this is already kind of, I would say, new, not old, because C-cube is still being demonstrated.
and Caterina.